general relativity, step by step. I've got these two expressions here for the x and the y components of acceleration of freely falling particles near my reference particle. I'm going to make a further simplification that alpha equals 1 and beta equals 0. So I'm just going to consider one polarization effectively. One polarization. It'll just simplify the mechanics. I'll do the next case. I'll do the beta one next, but I'll do this one. So alpha equals 1 and beta equals 0. And furthermore, I'm going to choose that v equals 1. You'll remember that v was oscillating. So I'm just going to pick was the oscillation term. So I'm just going to pick a component in time, a place in time where v was equal to 1. So it was in the positive, in its positive phase. So what have we got here? We've got ax equals v for my small thing times nx from this line here, and I've got ay equals minus v ny from that term there. Well, that's great. That's nice and simple, isn't it? Let's have a look at it and see if we can draw it. Just a minute, let me pinch in a little bit. Here we go. And what I'm going to do, there's my reference particle, that's my origin. I'm going to consider a particle there, particle there, particle there, and a particle there. This is my x-axis, and that's my y-axis. And I'm going to draw accelerations in a different colour. I'm going to draw accelerations in green, I think. So this point here, we've got no y acceleration because we've got no y component, and we've just got a nice positive acceleration away from the origin, and here as well we've got a nice positive acceleration away from the origin. Here we've got a negative acceleration, so we're accelerating towards the origin, and here as well I guess we're accelerating towards the origin. What about particles not on the axis? Let's just try and draw some of those. I've got a particle there, particle there, particle there, and a particle there. Notice how linear everything is. The acceleration is just proportional to distance away from the origin, which is quite nice. So that's why I'm choosing these little components here. Let me just draw in green. This one here is going to be a linear superposition of the acceleration at this point here is going to be down here in that direction there. This one here is going to be that direction. This one here, because this one, you see, it's a superposition or a vector addition of that and this. This one is going to go in that direction there, and this one here is going to go in that direction there. That's quite nice, isn't it? So we've got this nice little picture of how the accelerations, the local accelerations, work close to my reference particle. Now, of course, it's not just accelerating that way forever, because eventually the phase of our oscillatory component, which was here, eventually that phase becomes positive. This is just a sine wave. Yeah. So here, this little particle will undergo simple harmonic motion backwards and forwards, backwards and forwards. And this one here, backwards and forwards, backwards and forwards, backwards and forwards, up and down, up and down, up and down, up and down, and so forth. So if you build up a little pattern of what it looks like, it's pretty clear what it looks like. I'll draw it in orange, I guess. We've got this nice set of lines like that, which correspond to the motion of free particles, or the acceleration of a free particle at this point here is oscillating around a line which is tangential to this, to my orange contour lines here. Up and down and up and down and up and down. It goes like this. There we go. And anybody who does fluid mechanics will note that this is a stagnation point, or it looks very much like a stagnation point. There we are. And so that's why we originally called it the plus component, A plus, because it's in a plus direction. We can try and do the other one. Let's have a look at the other one. What we've done here is alpha equals 1 and beta equals 0. Of course, what I'm going to do now is to consider the other one. So what we would see, let me just pinch out a little bit, we would see that AX equals V times beta, oh no, beta equals 1. So that's V N Y, and AY would equal, from this formula here, beta nx, which is Vnx. Okay, so we've got a very different situation there. Let's see if we can draw this. Let me just pinch in a little bit. I'll draw my axes. Whoops. So this interface is misbehaving and it's driving me nuts. We've got x and y axes. I'm going to have my reference particle in the middle. I've got my little particles here, 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 and here. And I'll draw again in green the accelerations that these guys have in green. So what's this one here? That's got an x component. Oh dear me, what's this one got? That's got an x component, so it's got a y acceleration. This one is going the other way, isn't it? Because the x component is negative. There we are. We've got a nice little acceleration vector. This one here has... Yes, this one here has got a positive component, and this one here has got a negative component. What about this one here? That's going in, because it's a composition of this one and this one. This one here is going out at this particular point in its cycle. Obviously it's going to accelerate out and then it's going to oscillate around this line here. What about this one? That one's coming in, I think. Yeah, and this one is going outwards like that. So if I were to try and draw the pattern of how the whole plane looks, it looks, oops, that's green. The whole pattern looks. Let me go back to black, or at least I'm trying. So the whole pattern looks like, let me draw it in orange. Yeah, it looks like that. Bit tricky to draw. It looks like that. Yeah, I'm not drawing it particularly well, but we can see the difference in the two phases. So this is the alpha component here, and this is the beta component here. So that explains what I was trying to say before, but I couldn't quite say it clearly because I hadn't drawn the other polarization. That's called the A plus component because it's forming a plus here, and the beta is called the A cross component because it forms a cross there in the middle. I've not drawn that very well. What I might do is try and draw a nice vectorized diagram in R for you, and I'll show you the next time. So that is the effect of a gravitational wave on freely falling particles in free fall near a reference particle, which we use to measure our accelerations relative to. So I think that's quite nice. I'm going to stop there. Stop.